Sir, I've got college match, sir. Cricket match, that is why.
College match, cricket match. You got the permission?
Yes, sir.
Who has given the permission?
Principal, sir.
I'm not able to hear you.
Principal, sir.
Okay, good, ma. Very good. So when principal sir has given the permission, there is no issue from my end. Okay. So please be online. Okay, let me start sharing the screen. Okay. So good morning to one and all. Once again. So, see, in the previous class, we have discussed about the low pass filter. Okay, low pass Butterworth filter, where we are going to pass, or it's going to permit only the low frequency component as the output, even though we are having the different frequencies. Input may be having n number of frequencies, but the output of the filter is going to transmit only low frequency component. So I already written the waveform also. Waveform, I'm not finding the waveform here. Let us check it out. Yeah. So this is the waveform where the low frequency, I think those are sitting that side. Let me. Only the low frequency component is transmitted. Once it reaches the FH, that is cutoff frequency, we call that one. FH is a cutoff frequency. After that one, the gain of the amplifier is keep decaying or decreasing, and it will reach to zero. It's going to reach to zero. We call that one as 3 dB frequency or minus 20 dB frequency. We call that one. So as the cutoff frequency. The cutoff frequency what we are going to get is a 3 dB frequency. Okay. So we will be having a gain, that is AF, we call that one, V0 by Vi. Generally it is V0 by Vi. AF is given as, since we are connecting the input to the non-inverting terminal, the gain is 1 plus RF by R1. 1 plus RF by R1. I think all of you know that one, no need to write it. I'll just revise this. AF is 1 plus RF by R1. This is the gain of the low pass filter when it is connected to, when the input is connected to non-inverting terminal. Okay. But when the input is connected to inverting terminal, what is the gain? Minus RF by R1. This is for inverting the input. This is non-inverting input. Okay, so V0 is equal to AF into Vi. What are we are going to give that one? But since we have connected the RC component, Vi is going to be changed to V1. We have connected RC as the before giving the input to the op-amp. The Vi, what is the actual input we are giving with the frequency that is passing through the RC circuit, where some drop in the voltage comes into picture, some change in the voltage comes into picture. So Vi, the actual input Vi is changed to V1. Is changed to V1. In the first order I am talking about. In the first order, lower, that is low pass filter, low pass Butterworth filter. When it comes to second order low pass filter, second order, we have the two sets of the RC component. Two sets of the RC component. Let us see how exactly it looks into. So the circuit diagram, you may be, okay, let me increase the size. Yeah. Is that visible? The circuit is visible. Here, excuse me, we have two resistors and two capacitors which are connected to the non-inverting terminal. Are you able to observe that one? Non-inverting terminal, whatever is displaying on the screen is little bit rearranged, and rearrangement has been done. I will rewrite the circuit on board so that it will be easy for you. How we have followed the first order, no? Based on that only we can write the second order also. You know this first order circuit? First order circuit, you know that one. Let me write that circuit first, then based on that we go for the second order. We have a op-amp, we have a non-inverting terminal. For the non-inverting terminal, we are having a resistor and a capacitor which is connected. And for the inverting terminal, we will be having one resistor, that is R1, and second resistor, that is RF, that is feedback resistor, and we will be having RL, RF, R1, and this is your R value, this is your C value. This is with respect to first order I am talking about. First order. Small change comes with respect to that. I am not given the input because I need to give one more RC circuit here. One more RC circuit has to be given. So what they have done in this circuit, R, whatever the R has been given. So this is the non-inverted terminal. There I have written at the bottom is the non-inverted terminal I have written over there because with respect to I am referring with the previous circuit. I am referring the previous circuit. So R, what is been written there on the board, it is R2. Okay. Previous to that one, I need to have one more resistor. And before R2, I need one more capacitor which is not directly grounded, which has been given to the your output. It's been given to the output over there. We have the RARP, that is R1 and RF is there. R1 and RF which is connected to non-inverting terminal. One is connected to inverting terminal grounded, other one is feedback resistor. Okay. This RA what we are getting, which is written as RF, RB what we are getting here, that is written as R1. Okay. So I am making this as ground, connected ground. Now I need to have one more resistor here. One more resistor. This is R2, this is R1, and for this one I am giving the input signal. Okay. Here, one more capacitor, the second RC circuit. The C, what I am having, either I can write it here. Okay, let me have more clarity. C, two parallel, but this is not grounded, which is been given to the output terminal. Other end of the capacitor has been connected to output terminal. So same thing. Other end of the capacitor is being connected to output terminal. RF is coming from top and C is coming from bottom. Here they have just reversed the op-amp over there. In the display, op-amp has been placed top down up. That is vertically it is tilted. Vertically it is tilted over there. Same thing which is given here. Now I can write that is inverting terminal, non-inverting terminal, R1, R2, C1, C2, and this is your V in, and this is your V1. Simple. Okay. This is what is being given in the textbook. Either you can refer the textbook or you can refer the online. Both are same only. Okay. So on these two, plus 15 volts, minus 15 volts. Pin number 2, pin number 3, pin number 6, 7, 4 with respect to mu A741. Kindly note down. Do it fast. And we will be having V0 also. V in has been given, and we will be having V0. Any confusion? So I think this will be easy, which is written on the board will be easy because two RC circuit are in parallel. It will be easy for you to measure that one. First R1 C1 is for first order, R2 C2 is for second order. Done? Completed? Yes, sir, no. We have got one more person, Sunil. Anyone is there by name Sunil? Good morning, Sunil.
Good morning, sir.
Are you able to see the screen? Wait, sir, I will check it. Sunil,
Yes, sir.
are you able to see the screen?
Sir.
The screen has been shared with you.
Yes, sir.
Are you able to see me?
Yes, sir.
Yes. What you can see on screen?
Sir. Filter, sir. Awesome.
Yes, sir. Anything has been shared? Any material has been shared on screen?
Circuit, sir. Only one circuit.
Can you repeat?
RC network circuit, sir.
RC network. Okay. My voice is clear? It's okay. I don't want to waste the time. Okay. Any confusion? Two RC circuits are going to be used with the input. When you are passing the input, Vin is the actual input with some frequency. It's going to have the frequency. We can select the frequency, or we can keep changing the frequency as we were doing in our RC coupled amplifier. In RC coupled amplifier, what we were doing, we were keep on saying increasing the frequency from 10 hertz or 100 hertz to some around 200, 300 kilohertz itself. Where I am getting the frequency band, I am going to get that one. Where you are finding the what is the V0 by Vi, we are able to find the gain. Finally, we are able to find the bandwidth also. Here also same procedure we are going to use. Instead of this transistor, we are having the n number of transistor integrated together as an op-amp. N number of transistors, resistors, capacitors, all those things, we put them molded in one single IC that is called as the operational amplifier. Okay, where I am able to get the required frequency only, and other frequency can be omitted or discarded. Okay, so what is the gain of the amplifier? The gain of the amplifier, as we all know that one, since we are connecting to a non-inverting terminal, AF is given as 1 plus RF by R1. Because I have given RF by R1 in the circuit on the screen, they have given R2, RA, RB they have given. RA, RB. RA is the feedback resistor, RB is the input resistor, where RA divided by RB is what is been given on the screen. Gain of the second order filter, second order whatever filter is 1 plus RA, RB, which is given on the on screen. But in circuit, we are using is RF by and R1, same thing. Frequency, FC, the cutoff frequency, where we were using 1/2 pi RC. We were using 1/2 pi RC now. Okay, here we are going to have two resistors and two capacitors we are using over there. So 1/2 pi root of R1, R2, C1, C2. R1, R2, C1, C2 is what we are using. Same thing, we can go for that one. Then if resistor and capacitor values are the same, assume that when two capacitors and two resistors we are using, which are same value, C and C1 and C2 is same, so you're going to get the C square, and R1 and R2 is the same, we are going to get the R square. Root of R square C square will be RC only. Root of R square, because if the resistors and capacitor what we are using is same value, then the root of R square C square will become RC itself. So whenever you want to find the cutoff frequency, whenever you want to find the gain, you supposed to select the proper RC value. The proper RC value if you select, then the particular frequency only we are able to transmit that one. If you, in the previous class also I have discussed about how to design a low pass filter. There are 4 parameters have been to be selected. First thing is what frequency you should be considered as a cutoff frequency. That means up to what frequency you're supposed to transmit. Okay, so I'm having a frequency from 0 to some around 200 kilohertz. Even I can go for more than that. You are having a function generator. Have you used the function generators in your lab? Okay, up to where you keep on increased your frequencies. RC coupled amplifier, you have done that one. Any other application you have done that one where frequencies keep on increasing? Any other experiment you did in the lab where the frequencies keep on changing? BJT, that's what. BJT is the RC coupled amplifier I'm talking about. BJT is the experiment name. What is the full question name? RC coupled amplifier using BJT. That is the question. RC coupled amplifier using MOSFET. RC coupled amplifier using JFET. RC couple. We are using the resistor and capacitor as a coupling. I know that one. I told you what exactly coupling is. You are coupling the frequency. You are coupling the input signal. Okay. To what? To the transistor. Which transistor? It may be a BJT, it may be a MOSFET, it may be a JFET, it may be different types of transistors. Here also we are using the RC coupled only. Instead of BJT, we are using the op amp. Okay. So take an example. I have the function generator which is going to be in the range of 0 to 30 megahertz range. I can start from 0 frequency and I can go up to 30 megahertz range. Okay, the input is that much heavy frequency I am having over there. But I should design a filter such a way that I have to start from 0 and my frequency it should be only 10 kilohertz. Means I should select the cutoff frequency that is 10 kilohertz. Very first design principle is what should be the cutoff frequency of your filter. First parameter. Once you know the cutoff frequency of the filter, then you should know capacitors. Even though in the labs, that is academic labs, we are having the decade capacitance boxes. Heard about it? Decade capacitance boxes, decade resistance boxes, decade induction boxes will be there. Okay. In our academic labs, we will be having the decade capacitances, where variable capacitances are there. But when you go for the industries, they won't use the variable resistors. Sorry, variable capacitance they will not use. They will use the variable resistors. Can you give me a simple example where variable resistors are going to be used? In our daily life, we are using that one. In our daily life, we are using variable resistor. Yes. Potentiometer. What exactly a fan will do? You switch on. With that switch, we are going to have a regulator. Fan regulator. There are 2 different types of regulators are there. One is a regulator which is going to have where we can stop it each and every time. But there is one more regulator is there. Easily you can rotate it over there. Okay, you may be having a regulator. Any regulator is there working? Any regulator is working? We have very good students. That's why it's like that. Okay. See, if it has been working, I would have shown you. Very simple. Initially, it is having a very high resistance. very high resistance where it is not permitting the current to flow. It is not permitting current to flow. Even though I switched on, the switch is on, the regulator, which is kept for very high resistance, infinite resistance, you assume that one, infinite resistance, open circuit. It is like it will be there. Which is connected like this. Okay. Initially, this it's a switch, simple switch. We are going to have 1, 2, 3, 4, 5 off. You may be handled. In the regular it will be displaying like this. Okay. Initially, it is connected to off. It is connected to off. That means current will not flow. There is a point where it is open circuit. Now what I will do, I'll turn this regulator where it is going to get connected here. It's connected here. Once it is connected, fan will rotate. Fan is going to rotate now because here it was open circuit. Here there is very high resistance. Open circuit is very high resistance. Here it is switched to the next position where the resistance value from infinity it is reduced to some around 100 kilohertz, 100 kilo ohm. Assume 100 kilo ohm. Okay. Since this resistance is 100 kilo ohm, current flow is very low. Current flow is very low. So fan rotates slowly. When I put this point to here, 100 kilo ohm to 10 kilo ohm it will be reduced. What happens? Resistance is keep decreasing, current flow increases. As the current flow increases, motors start rotating faster. If I rotate this one here, then 10 kilohertz to 1 kilohertz, 10 kilo ohm to 1 kilo ohm is reduced. Okay? 10 kilo ohm to 1 kilo ohm. So resistance decreases, current flow increases, fan rotates faster. Similarly, I can point to the last one where it may be 100 ohm. It may be 100 ohm. There should be some resistance. Don't say that one 0 ohm is there. Okay? There should be some resistance. So as the resistance decreases, current flow increases over there. So a simple potentiometer where it's going to give the how exactly we can go for that is frequency. Similarly, the frequency also. Even what you are going to use the knobs which are there in your function generator, CROs, and also RPS, regulated power supply. All the knobs what we are using over there, no, to increase or decrease the voltage or increase or decrease the frequency, all those things works with the same principle where I am going to reduce the resistance value as I keep rotating clockwise, resistance value reduces. As I keep rotating anti-clockwise, resistance keep increasing over there. Simple potentiometers. Some of them are freely movement, some of them are it's going to get struck, means step by step it's going to increase the. So first point is select the frequency properly. So I told you 10 kilohertz only I need to select over there, 0 to 10 kilohertz. Okay. So what happens? 0 to 10 kilohertz is going to transmit. After 10 kilohertz, decreases. Whenever you are designing the filter, select the frequency. First thing, once you select the frequency, as you know that one FC is equal to 1 by 2 by RC. I have selected the FC. Then I need to select RC values. Okay. Capacitors, as I was saying that the industries, most of the time we go for the fixed capacitance, we don't go for the variable capacitance. So select the capacitance. It should be in the range of less than 0.1 microfarad. Should be in the range of less than 0.1 microfarad whenever you are designing the capacitor, any filter, anything. So I may go for 0.1 microfarad, or I may go for 0.01 microfarad, I may go for 100 nanofarad. Anything is possible. Okay, 100 nano or 10 nano, like this I can go for that one. Once we select the FC, once we select the C, then it is easy for us to select the resistor. Okay, a variable resistance we can go for that one. This is fixed, this is fixed, this I can vary. This I can vary. But if you want to go for different frequencies, fix this C value, keep varying the resistance value, you are going to get the different frequency also. That's why frequency may be like this or it may be like this also. That is what has been given in your previous waveform where different cutoff frequencies you can go for by selecting the different R value over there. Okay, different R value. So we know what should be the gain of the frequency filter and what is the frequency of the what is the actual frequency cutoff frequency of the filter. Then based on that one, we are going to select the R value, C value. So this is the second order filter where we will be having two RC circuit. Two RC circuit will be there itself. So in this one also, how to design the second order filter. The first one is choose the value of the high cutoff frequency, that is FC or FH, whichever you are going to call. Simplify the design calculation, that is R1, R2, or both should be same. R1, R2 both should be same, so that it will be easy for you to simplify that one. Similarly, C1, C2 also. C is supposed to be less than 1 microfarad. Less than 1 microfarad or 0.1 microfarad. And finally, you can go for R is equal to 1 by 2 pi FC. R value, you can go for it. So this is what is required whenever you go for the selecting the frequency. So select designing your filter.